All right. I hope it's showing up well.
Yes, yes, we can see your
Yes.
screen.
Wonderful. So thanks, Kobe, for the intro. My name is Shachar Menashe. As Kobe said, I'm the Senior Director of Security Research at JFrog. So I manage several teams. What we do is in-depth CVE analysis, which is the topic that I'll be concentrating on today. But some other things that we're doing is finding zero-day vulnerabilities and fixing them in open source, finding malicious packages, both unknown ones and known ones, and disclosing them. Basically everything to do with security research. But today I want to talk about our CVE analysis aspect, and actually a problem that plagued us and plagued us as researchers, and I believe that plague a lot of researchers and PSER teams, that well, basically you're using a software composition analysis, or you're going on CVEs completely manually, and you have a list of components, and basically you're going over the CVEs and you're seeing a ton of CVEs, but you're actually starting to understand that not all of them can actually be exploited in your instance. This is a very well-known issue in the researcher world, and I wanted to open it up and talk about how you, when you look at a CVE, can spot these little fallacies that will show you, oh, there's actually more to see on the CVE, and the CVE may actually not be vulnerable on all configurations, and trying to understand on which configurations it will be vulnerable, and how rare or not rare these configurations are. So we'll talk about, first we'll define the basic way to evaluate CVEs, the way that almost all software composition analysis tools use. And then we're going to dive a bit into where these software composition analysis tools and even manual researchers, what they're not looking at and what you should be looking at when you're evaluating CVEs. So let's start with defining how the basic CVE evaluation usually works. So let's say you're doing a manual audit, or you're using a software composition analysis tool. So 99 times out of 100, what that does is, or what you're doing manually, is you're creating a component list of every component you have. So Python packages, JavaScript packages, Ubuntu packages, binaries on the device. You're creating an entire component list, and you're determining the version of each of these components. And then when you have that data, the component list and the versions, basically you're correlating it with various databases of known vulnerabilities. It's usually CVEs, but doesn't have to be CVEs. For example, Red Hat use their own identifier, and GitHub use their own identifier, etc. But CVEs are the most well-known ones. So then you can just correlate. You can say, okay, I see that there's a CVE on the Docker tester package for NPM on versions this and that. So you cross-ref it with your component list, and you're saying, okay, I have Docker tester version 1.2.0, so I'm affected by the CVE. And that's the basic way that basically all these SCA tools work, and also the basic filtering that you do manually to try to determine what CVEs your image is susceptible to. It could be a Docker image, a dump of a file system, etc. So in this presentation, I actually want to go over various cases where showing this CVE as vulnerable would be a false positive, and I want to show you how to look out for these cases in various types of CVEs. So we'll go over 3 major examples and examine what's hidden in the CVE data. Sometimes it's more hidden, sometimes it's less hidden. But I want to show you the broad categories, at least as our research teams see it. So the idea is that I'm not just uploading, this Docker tester package in a specific version. I'm not just uploading it to some software composition analysis tool, I'm uploading my entire file system or Docker image. So I have additional data on the context of where this package is running and not just the package itself. And that will allow me to determine to an extent if this CVE is actually exploitable in this context. All right, so let's look at a first example. So first, let's look at code prerequisites that CVEs might have. And we'll look at these prerequisites, and then we'll try to figure out how common all of these prerequisites are in terms of all the CVEs that we're seeing. So let's look at CVE 2021-23337. So basically, it's a vulnerability in the Lodash library. It's a utility library for in NPM, so Node.js utility library, and it says Lodash versions prior to 4.17.21 vulnerable to command injection via the template function. And of course, you get the CPE for that CVE. So my question is, and this is the question that will be recurring through all these configurations, is okay, so if I have Lodash and it's 4.17.20, can I immediately say that my machine is exploitable to the CVE? So I'll ask the question and answer the question, and this will be kind of our recurring case in our presentation. But so for this example, the answer is no. And this is actually relevant for all library CVEs. So library CVEs are always what we call context-dependent CVEs. So even if the CVSS might say, yeah, it's remotely exploitable, it's actually a fault in the CVSS, and it's not correct to say that. Because for this vulnerability to be exploitable, you must have some other code in your environment that imports Lodash. And in this specific case, uses the template function, because the CVE is only on the template function of Lodash. It's not enough for you to just import Lodash. And the most restricting case here is that you need to pass attacker-controlled input to a specific argument of this function. So here on the right-hand side, we can see code that is vulnerable to this issue, because first of all, it requires a Lodash, and then you can see it calls the template function and it passes the name argument. And we can see that name is coming from remote input, for example. In this case, it's a function argument. So we're not going to dig deeper and see if it comes from a socket or anything, but supposedly it's from remote input. So only in these kind of cases it will be vulnerable. And the idea is that once you see a CVE that's CVE in a library and it's not a daemon or a client or something like that, immediately that makes the CVE context dependent, and you cannot say for certain that that just by having the package installed, the CVE is exploitable. You always have to use a specific function, and usually you also have to pass attacker control data to it. So this is, again, for library vulnerabilities, this will always be the case. You must have someone that uses the library, some other code, either first-party code or third-party. So this is not the only code-based prerequisite, actually. There could be other prerequisites which are like kind of hidden in the CVE description. One is just if the vulnerability was backward patched in that specific environment, someone just patched it, so that could also be the case. The second one is what we saw. Is the vulnerable function even called? And was it called with a specific arguments that triggered this vulnerability? So it could either require attacker-controlled arguments, and some arguments might need to have a specific constant. Like, for example, the third argument must be true or be equal to some specific string. In some cases, there's actually a different function when, if you call it, it mitigates this CVE. For example, let's say there's a SQL injection CVE. There could be a different function in the same library that, if you call it, it mitigates the CVE. The problem is that this data will not always be present in the CVE description. You usually need to go to a technical write-up if there is something like that, but try to look out for it because sometimes it will be. If you remember in the CVE description we saw, also, sometimes it's not a vulnerable function that's vulnerable. It could be a vulnerable class that's vulnerable. So you need to look out for first-party code that inherits from that class. So that was the first example. Now let's look at a second example. So now I'm looking not at a library vulnerability because we said library is context dependent, and I want to move on to a different example. So let's look at the daemon vulnerability. So with a daemon vulnerability, in some cases, there's a daemon running, and if the daemon is running, the vulnerability is exploitable. So there's actually, in some cases, you don't have to look deep, but in many cases you do. Okay, so let's look at a different vulnerability, and I'm not going to go over the whole description, but basically it's a vulnerability in Apache Cassandra. It's a very well-known database, like a distributed database, like a SQL-based database. And there's another vulnerability here, and again, it says that it's a remote vulnerability, etc. And we're gonna ask the same rhetorical question: is okay, if I have Apache Cassandra installed in the vulnerable version, am I vulnerable? And this time it's a daemon, so it might be. Again, the answer is no, because we're trying to elaborate here. So in this case, the CVE was actually very descriptive, which is also a bit rare, but there definitely might be a case that even with a daemon vulnerability, it's only exploitable in a specific configuration. And actually, I would say this is not a rare case, but it's even the common case. Because usually, when you're running a daemon, the default configuration is very highly audited, but and especially if it's a maintained daemon, which is older, it's already been audited a few times, it's open source. The default config is always more heavily audited than some niche configuration. So usually, if it's a vulnerability in a daemon, which again is like a robust project, it's probably going to be in a rare configuration, or at least not the default configuration. The problem with CVEs and CVSS is there's no formatted field to say, listen, this is only exploitable on this and this configuration, or this is even context dependent. There's no fields for that. So even if the CVE reporter wants to say this information, it can only be said in free text. That's why currently you have to look out for these things in free text and researcher advisors, etc. Sorry, so I didn't elaborate, but specifically on Cassandra, this is only exploitable in a non-default configuration. There has to be a YAML file, and it has to have these specific configurations. So more examples of configuration prerequisites. Sometimes the configuration is even in compile time. Like you give a configuration in compile time, whether to include the code that has the vulnerability. For example, OpenSSL has 1 million of config options to support different protocols. It might be that OpenSSL wasn't even compiled with the vulnerable code. So that's one way. It's also very common in Linux kernel vulnerabilities because it's very modular. Sometimes there's a patch or a workaround, but the component isn't configured to take advantage of that. When we're looking at configuration values that enable the vulnerable functionality or not, we actually have to look at many different places. The configuration might be fed through environment variables, it might be fed through command line, and it might be fed through a config file like we saw in the Cassandra example. But even in a config file, it might be through a hard-coded path, or it might be through like a path that you specify through a command line or environment, etc. So even there's a lot of nuance to what you have to look for. But always, again, general tip, with a daemon vulnerability, I would always try to see if it's exploitable on the default configuration or not, because you're not going to get this information on CVSS. It's just, I wouldn't be able to specify it even if I wanted to. So currently you just have to look for it in the free text. Okay, and the last example that we're going to see is a prerequisite on the environment itself. So not really a configuration or code, but here there's a vulnerability in Apache Hadoop, just an Apache RDP server, and it supports an untar function. So here, it's not a library that calls this function. You can actually send a request to the server and make it untar all sorts of things and extract it to all sorts of places with the specific request. And again, the question is, here it's also a daemon, so it's not going to be a library. And the question is the same question. Okay, so I have Apache Hadoop and 320. Is my machine 100% vulnerable? And here it's not a matter of configuration. Again, I hope you read a bit about the description yourself, but here it's also, I deliberately chose descriptions that are more obvious, just of course that we can see we can see obvious examples, because the harder ones are harder to explain. But here it's very obvious from the description that actually Hadoop can be installed both on Windows and Linux and other operating systems. And actually the vulnerability only manifests on Windows and not on Linux. On Linux, there's checking code, but it only did a correct check on Linux and Windows. So because there's different code branches for different environments, it's something, it's another thing that you have to check regarding the CVE. So this time it was explicitly specified in the CVE. That's actually less rare than the previous examples. Like a lot of times, if it's a configuration, if it's an environment prerequisite, it will be specified because it's a bit more rare for the code to actually have different branches per environment. Again, there's no CVE formatted field, so you have to look for it in the free text. Usually, like most of the CVEs are exploitable under all environments. So like I said, this is a bit more rare than the other ones, which are very common. So because it's more rare, it's usually specified in the CVE text, but it doesn't have to. So let's look, just to look at some others environment prerequisites. So again, the operating system. So here we saw different code that runs on different types of operating systems, but it can also depend on the distro. Like for example, Debian and Ubuntu Linux have a lot of different default security mitigations. So what works on Ubuntu usually might not work on Debian, which is a bit more hardened. The bit level of the operating system, like if a lot of vulnerabilities work on 32 bits, but not on 64 because of address space randomization and things like that. Something obvious that sometimes is missed, like, is the vulnerable process even running in this environment? Is it running on startup? Can it be triggered by some internal or external event? If it's a daemon, maybe the vulnerable port is blocked by a firewall. It could be an external firewall or a host firewall like IP tables. Some vulnerabilities, for example, like PwnKit, they depend on a specific binary from the package to be installed on the system. So it doesn't matter if you have an entire package, like a package installed, you need to have a specific binary from that package, and not all software composition analysis tool account for that, of course. You might have like an OpenSSL client, but you don't have the OpenSSL server. That's actually a very common one. So that's also an environment prerequisite. And sometimes you even need special privileges on the vulnerable binary. If it's a local privilege escalation, it might only be exploitable if the vulnerable binary is a setuid. And if it's not setuid, it won't be susceptible to local privilege escalation. For example, the ghost vulnerability, also a very well-known one. So these are just these are all the example categories this is the way that we chose to split it, and I think that actually all the CVEs fall into one of these categories. So for us, it works very well when researching, and also when writing automated code in our system to categorize for all of these. But you know, a CVE from 2022, I think it's pretty safe to say that in general, it will not be exploitable in the default configuration without any context. You know, there are outliers like log4shell, for example, which even though it's context dependent, the context was so common, like you have to log a message with attacker input, that you could almost say, yeah, it's exploitable in default config without any context. But these are, you know, things that break the internet and are very rare. For 99.9% of CVEs from 2022, this won't be true. So like I said before, for library vulnerabilities, there has to be code that uses the library actually in some vulnerable way. And for client daemons, it's usually the default config and context is audited to a much higher degree. So it doesn't, usually the vulnerabilities don't affect the default config and context, unless of course, you know, it's a very new daemon and it's not robust yet. So these are kind of operational risk issues. So basically, almost from our perspective, if you're using the basic CVE evaluation, you're almost always going to get a false positive in your environment, because most of these things are not exploitable by default. So I'm just gonna repeat very quickly what I said before. Our tips for this deep CVE evaluation is, if it's a library vulnerability, just, you know, check if the component is a library or it's a client or it's a daemon. If it's a library, look for which functions specifically are vulnerable and which values in the arguments are vulnerable. And one thing to look out for, and one thing that we use in our severity ratings, does it even make sense that this function will receive outside input? Like if it's an internal function, not exported one, like what are the chances that it will even receive input from outside? So then the severity, the actual severity will go down. In CVSS, it will still be high because CVSS doesn't look at all these things, but just tips for researchers. And on client daemon vulnerabilities, you have to figure out what is the specific configuration that is actually vulnerable. And if it's the default config, then we rank it much higher, for example, in our research and in our security tooling, JFrog X-Ray. A specific thing to look out for in the CVSS is that vulnerabilities with high attack complexity, it usually means that the researcher can't create an exploit that works on all targets. The researcher has to do some research on, like, per target and understand specific context where, for example, the vulnerable function is called, and then only build an exploit made specifically for that target. So if you see attack complexity high, it usually means it's not going to be a drive-by exploit, and it's gonna require a targeted attack, basically. So that's something to look out for. And what it says on the CVE research side is that you have to understand if a specific function has to be called for the CVE to be exploitable, or specifically what target specific information is relevant. And then if you're blue team, for example, after you figure that out, you'll know if you're vulnerable. But this is like a highlight for you to say, okay, I need to look at this deeper. It's not, if attack complexity is high, it's 99.9% of the cases, it's not exploitable on the default config and on the default context. Yeah, so that's pretty much it. We have a bit more time for Q&A. We have a minute to spare, so I'll be happy to answer any questions on the chat or Q&A.
Thank you, Shachar. There is one question in the Q&A, if you can address it, please.
Yeah, so I'll read it. For library vulnerabilities, how to judge whether it is vulnerable for those third-party library usage. For example, if I include installed Node.js, will it be considered exploitable for those transitive dependency libraries? So I'm assuming, so if I'm understanding the question correctly, I'll try to interpret it, but it's a very good question. So there might be a case that there's some library vulnerability, but actually it's exploitable by default if I'm using some other third-party library. So for example, let's say there's a command injection in Lodash, like I said before, and there's a different third-party library, for example, Shachar dash or whatever name, that uses Lodash, but calls exactly the specific function that is required for command injection. So that's a very good question. There is no easy way actually to determine that. Usually what happens is one of two things. Either the other library sometimes opens a separate CVE for that and says, we opened CVE this and that, and we opened this because we are vulnerable to, the original CVE. And in that's the easy way, and then you will just catch that CVE on, the parent third-party library. But let's say that there wasn't a CVE opened on that. What I usually do, I search for the original CVE name in GitHub and see if there are issues opened on the parent third-party library that says, by Dependabot or things like that, that say, okay, we fixed it because we are actually vulnerable to it. It's a really good question because it's a tough question. Like, you have to look manually in most cases. Sometimes there's a separate CVE being opened on the parent third-party library, but sometimes you just have to look for yourself. Yeah, it's tough.
Okay, great. Thank you, Shachar.